Have you ever wondered how these self-driving cars build a centimeter accurate 3D representation of the world around them? How do these humanoid robots see the world around them and how do they map them? How can you build aerial robots that can see through the distance and build a map so that they can do obstacle avoidance perfectly? Let's delve right into the world of factorgraphs today. So let's talk about SLAM, or simultaneous localization and mapping. The idea is that we are a robot, we are in the world, and we do not know how the world looks like. We also want to know where in the world we are with respect to this map. So just by looking around and moving around, we can build a map and sort of put ourselves in that map. And that's the localization part, putting ourselves in the map. And the mapping part is basically reconstructing a map around us. So let's start with a simple example. Let's have a 2D world. In this particular case, it spans from minus 20 meters to plus 20 meters in X and Y direction. So it's a 2D world. And we have these landmarks which we can identify with numbers. Note that the robot does not see the entire map or entire landmark set at once. It only has a limited field of view. So let's define our coordinate axes as follows. So X is positive horizontally and Y is positive vertically. Notice that the 0, 0 or the origin of this world is somewhere in the center of this map. So the world is made up of landmarks, and the landmarks are unique and numbered. And each landmark, which we are going to denote by LK, is given by the position of X and Y, and also the tag of that landmark, which is K, which is denoted by the number there. And the coordinate is represented in that map. So let's say the robot starts at minus 10, minus 10. Remember that the robot does not know where it is in the world. It does not know it's starting at minus 10, minus 10. It's just an arbitrary choice. And the robot basically has odometry which says, okay, you have started at 0, 0. For all practical purposes, the robot is starting at 0, 0 in its map origin. But this map origin is technically in minus 10, minus 10 in the world. So the robot state is given by 3 numbers because it's a 2D robot. It's a fairly simple thing. We are going to denote that with this boldface X, which has 3 numbers. So it has the X coordinate, the Y coordinate, and the angle the robot is rotated at where it's facing. Remember that the robot does not have a 360-degree vision, as we will see in a second. So that's why it needs 3 things. So in this particular case, we are defining the coordinate axis as the same as the world frame. So it's X to the horizontal direction, Y to the vertical direction, and a counterclockwise rotation is basically denoted as positive angle theta. So since the robot state varies with respect to time, we're going to denote it as X subscript T, where we can put individual subscripts for each of the elements X, Y, and theta. Or we can put the subscript on the entire thing as shown here. So for our sensor, we will pretend that it's either a wide field of view camera or it is going to be a LiDAR with 120 degrees field of view. And again, remember that the angle is denoted this way. The robot has a wide field of view camera or a LiDAR with 120 degrees field of view. The measurement model is simple. The robot does not perfectly identify every single landmark. So instead, what it does is this. So at XT, the robot observes LK landmarks where K denotes the individual landmark IDs. The sensor is not perfect, hence you will see a landmark with a probability of 0.95. So it's 95% going to be accurate to detect that landmark. In this particular example, you'll see the ones which are detected as the blue ones and the ones which are missed as the red ones. So you'll see a simple missed landmark here. And the measurement of where the landmark is with respect to current robot position is also not perfect. It's going to be denoted by this measurement MTK, wherein is the measurement at time t and for the landmark K, and you have the X and Y coordinates of that. Remember that this measurement MTK is noisy and can be thought of as drawn from a normal distribution with the mean being centered around the actual value and with some covariance. And this is what the distribution is going to look like. So essentially the Gaussian distribution is telling us is that we have a high likelihood of getting the landmark right and a very low likelihood of getting the landmark wrong. So that's all this is, right? And the robot is moving around in the world. So at robot at time t is equal to 1 is going to look something like this. So we were at time t is equal to 0. Now the robot has moved. If we zoom in a little bit, this is what it looks like. Since the robot is on the ground, it has wheel encoders, and it basically has some odometry source, which is not perfect, but we know the odometry between time t and t plus 1, and we are going to utilize that. And this wheel encoder can also be thought of as a noisy wheel encoder, which is again drawn from some normal distribution where the actual odometry is O hat, and we have some covariance with this. This covariance essentially represents something like wheel slip or the encoder being noisy and things like that. It's all modeled into that. So after multiple steps, like let's say 5 steps, in this particular case, the robot has taken 5 steps, and we basically want to perform what is called the SLAM problem, as we discussed before. The SLAM problem is as follows. Given the initial pose x1 or x0 and the odometry at between time steps t to t plus 1 and the landmark measurements at every time t and for k different landmarks, we want to obtain these landmark locations lk and the robot pose xt. Obtaining the landmark locations with respect to each other is basically the mapping part. Obtaining the robot pose with respect to these landmarks is basically the localization part. Since we are trying to do this together, this is called simultaneous localization and mapping. So this is what the zoomed in picture looks like. We essentially want to portray this as a mathematical entity and an optimization problem, which we will see in a second. Remember that we saw this entire thing as basically a Bayesian framework because we estimated each of these noise models as a Gaussian distribution, and we said that we can portray this as a Bayesian network. So the Bayesian network is going to be as follows. So we basically have our robot state x0 in the bubble, and we basically have landmark L7, for example, and we have a measurement M1, which we are seeing the landmark at state x0. Of course, we can also see multiple landmarks like this landmark 16 and with the measurement M3, right? And we basically have a time varying quantity of these states. We go from x0 to x1, where we can see different landmarks like L7 through M2 and so on. And we have this whole graph for like multiple time steps. We essentially want to say that all of this is correct. What is the maximum probability that these things are right, so that the right numbers for the landmark values and the states, given that we have these observations. That's what we are trying to do here. So we essentially want to obtain the trajectory and all these like landmark locations, which we have seen in this local map. The motion model is fairly simple. We are essentially saying that, hey, we have moved from xt to xt plus 1 or xt minus 1 to xt, and it's given through this Gaussian distribution, as we see here, with some covariance matrix. The measurement model is very similar. It's obtained through a different measurement. We have seen a bunch of these landmarks over time, and we know the covariance of the measurement based on the sensor modeling, and we know that this is what it should represent. We essentially want to maximize something called the maximum a posteriori, which is saying that both the motion model and the measurement model have to be correct together. What's the best value of the states and the landmark locations relative to that state? That gives us the best possible likelihood, right? And to do that, we are basically multiplying 3 quantities. One is the prior state, which is saying that we started at 0, 0. Then we have all the odometry measurements through the motion model, and that's the first step. We are assuming that they are all independent of each other, the noise is not correlated. And in the second part, we are seeing that it's all the motion measurement models, because we have seen these different landmarks at different points, and we know that all of these are correct. And this is what we are trying to do with the Bayesian network. All the Bayesian networks are great and can be modeled using something like a Kalman filter. This can be basically linearized to an extended Kalman filter and can be utilized to run this real time. They're often not that accurate because the real world is not Gaussian in nature. So instead, what we can do is we can model this entire SLAM framework as what is known as a factor graph. In a factor graph, we basically have a prior factor, which is you see in this like solid bubble, and we have state x0. We have these two landmarks L7 and L16 like before, and we have these observations through these solid bubbles, and we have different states as we saw before, right? In this particular case, any of these like solid bubbles is basically a factor which we are defining as a constraint and doesn't have to be a Gaussian distribution. So let's look at the math for the factor graph as well at a very higher level overview. The prior basically is similar. It's some probability distribution P. Again, can be Gaussian, but doesn't have to be. The motion model looks similar. It's again a different probability distribution conditioned on the previous state. And the measurement model is a different third probability distribution, which is basically the probability of the right measurement given the state and the landmark locations. What we essentially want to maximize is called the value of the graph, analogous to the MAP in the previous Bayesian case, where we are saying that all of these quantities are independent of each other, and we want some function of this to be correct. And this is analogous to the probability distribution of these things being right at the same time. And these are like given the states and the landmarks which we are trying to estimate. So we solve this as a big giant nonlinear least squares problem through either a MAP posterior, maximum a posteriori estimation, similar to the Bayesian graph we saw before, or we can use something like the negative log likelihood, and we can basically solve this. So these are both valid ways, and they can basically be solved in the scenarios we have seen before. I would urge you to watch the bundle adjustment video on a general brief idea of how nonlinear least square works. A little bit of a story time. When I was a master's student in 2015 at UPenn in the GRASP lab with Professor Kostas Danielidis, I was working on this problem called getting visual odometry or doing SLAM, and the challenge for me was to do SLAM in this glass building. This is the Singh Center for Nanotechnology, which is a part of UPenn, and this building is beautiful to look at, but it's a nightmare for people to work with on visual SLAM. Because it's a glass building, it has a lot of reflections, and you can see through the building, and the light inside is a very different color from the outside. So if you want to build like a map of this scene, or basically do odometry and know where you are with respect to this, it's a really hard, challenging problem, even with the fancy cameras we have today. The goal for me was, how do you do SLAM or visual odometry when you're trying to do an outdoor to indoor transition, which is going through the doorway, or indoor to outdoor transition where you're coming from inside the building outwards, right? You see these gates in the front. It was a really hard problem because of a lot of reflection, because the feature matching would not work that well. This was in tune with what was happening in the aerial robot industry at that time. I'm going to play a small video with the 3DR robotics at that time, which were planning to do some autonomous selfie smart shots. The goal here was like you have a building and you could basically click two buttons and it would take a beautiful shot like this. The goal for us was, can you do this outdoor to indoor transition seamlessly? And this was really hard. And the first step what we did was we basically looked at this Google Tango.
A prototype phone containing highly customized hardware and software designed to allow the phone to track its motion in full 3D in real time as you hold it. These sensors make over 250,000 3D measurements every single second, updating the position and rotation of the phone, fusing this information into a single 3D model of the environment.
We have a problem called navigation indoors, and it's a solution to that problem.
It tracks your position as you go around the world, and it also makes a map of that.
Imagine that you scan a small section of your living room and then are able to generate a little game world in it. I don't know of any other controller or gaming device that can do that at the moment.
Putting all this together, they pulled in experts from all around the world and got them all working on the same project.
Those are very high caliber people. Why?
So this Google project Tango was spectacular in the sense that like they used a simple smartphone grade computer and a couple of cameras and an inertial measurement unit and some depth sensors to be able to locate things in 3 dimensions and to be able to map them. So this was in 2014. They came out with 2 different products like this Lenovo Fab 2 Pro and the Asus Zenfone AR. We bought a couple of these Tango tablets and we tried to use this on the Sync Center you saw before. The problem was it just didn't work, right? It would basically have catastrophic failures in the loop closure. It would have catastrophic failures when we tried to map. It would work for a couple of steps and then it would basically go haywire because it couldn't match features. As you've seen, if you have not watched one of the previous videos on feature matching, I would urge you to watch that because that really shows why this problem is really complicated. So magically, if we have a SLAM or odometry system that works, the question was, how do you evaluate them? So we went back to the drawing board. We asked the question, okay, in this glass building, even if it worked, how do you know it's correct? How do you know if it's accurate, right? We were like looking at what is available on the market at that time. We looked at these things called the Pixie centimeter accurate GPS or the Qualsys system for motion capture outdoors. And for indoors, we basically had a Vicon-like motion capture system and we had Wi-Fi based localization indoors. The problem was at the interface, there was nothing available at that time. So that sent us back to the drawing board because there were papers which were claiming stuff like this, wherein they were like, oh, we will just do a loop around the building and we will look at the ends of the 2 points. If they intersect, that means the accuracy is really high. But the problem was it could have drifted all along the trajectory, but yet the accuracy would look really good. There were some other papers which basically would do multiple loops and basically look at how much the drift was, and they would claim that that's accurate. Again, that wasn't that accurate either. And there were some other papers which showed, hey, we are going to compare it to a product and show that we are qualitatively better. But again, that didn't really help us because as we saw, the Google Project Tango didn't work in scenarios which were really complicated, right? And there were also posts on Twitter at that time which said that we have solved the visual inertial SAM problem and people can work on new problems. Which again, as we found out, was not really true because this was a really hard problem to solve. So fast forward a few more years, there were better metrics which were developed. So for example, if you have a trajectory which is the ground truth, let's say we magically obtained this ground truth. Remember that we still haven't cracked this problem to get the ground truth for glass buildings. That's what we're trying to figure out. And we estimated it through some method, let's say like through a LiDAR or through a camera or whatever. The question is, how do you compare these two, right? So to do this, one way to do this would be to take both the trajectories, your estimated and your ground truth, and do an alignment between these two trajectories. If you align the overall trajectory together, this is called the absolute trajectory error. So in this, just to recap, you align the entire trajectory and estimate the error. The first question is, how do you align them? The answer is fairly simple. You assume a rigid transformation and you align. But if you're doing monocular based SLAM, which we already know that there is no scale information, which means that the map is scaled to an arbitrary unit, which you set, and there is no metric units, but your ground truth probably has metric units. So how do you do the transformation? In this particular case, you do what is called a similarity transformation, which means that scale is also a free variable. The problem with this absolute trajectory error is that it's sensitive to when the time occurs, time when the error occurs, which means that if the alignment is like not exact to that particular time, it will drift apart. So it's not that great. So, okay, so what can we do better? And this is what the math would look like. A slightly better way to look at smaller segment time pieces is what is called the relative error. The idea is that you pick small sub-trajectories and then you align each of them just like you did in the absolute trajectory error. And this gives you information about the short and long-term accuracy. The cool part about the relative error is that you can really know how well it is pieced together. And you can have handcrafted metrics on when to split this trajectory and so on. This trajectory evaluation toolbox is a work by Professor Davide Scaramuzza's group at the University of Zurich, and I would urge you to have a look at this. So going back to where we started this entire problem, there were outdoor datasets, there were indoor datasets, there was nothing which was in between, which means that there was no large scale indoor and outdoor transition dataset. Of course, we wanted to have ground truth, but for that we needed to have a dataset. We did not have either. So what we essentially wanted was have an outdoor to indoor transition in this crazy fancy glass building because it was visually really challenging even for LiDARs. And we were like, okay, how can we do this, which is also easy to set up and optically really challenging? So we said, hey, can we just buy a $30,000 multi-sense SL head and use the state-of-the-art LiDAR, inertial and camera odometry fusion at that time? And we bought one of these for $30,000 and it just didn't work. We had the same exact problems as any other system because it would go through glass and it was really hard of a problem for us to solve that. We also tried looking at the secondary reflections of the LiDAR and we tried to mathematically model that using uncentered Kalman filters. That did not work either because the signal to noise ratio was really poor for us. So we were like, okay, can we do something better? Can we go back to basics and look at visual fiducial markers like the April tag? And we thought, hey, can we just use simple one April tag to do this? As we found out, the accuracy was not that great. So instead, the solution we resorted to was basically have a row of April tags. We did not want to cover the entire scene with April tags because that's doctoring the entire scene. So we laid it in a nice way wherein we could like strategically place it in a way that like it's minimal coverage, but it's just enough for our solution to work. And to add to the solution, what we said is we wanted to increase the field of view of the camera setup. So we had 3 different GoPros. So we obtained about 270 degrees field of view for the sensor. So we could see more April tags at once. Again, we came up with another challenge. Placing this April tag in the building was pretty hard. So we basically, because we increased the field of view, we were like, okay, we can sort of solve that problem. But the other issue was because the field of view common between the neighboring cameras was so small, calibration was really hard for us. So instead what we did is we made a giant calibration target right outside the grasp lab. We basically had a wall full of April tags, which we stuck. And because the wall was so big, we could actually see some amount of April tags, which are common between the 3 cameras. We utilized what is called a factor graph for doing the calibration. We came up with our own custom calibration procedure. We will see this in more detail in a few more minutes. So the idea was very simple. We wanted to find the pose in the rig frame. The rig frame was the center camera, and we wanted to find the other 2 cameras in the center camera frame. And we said we have constraints that we have the image coordinates, which we know. This is what it looked like. And we basically wanted to estimate this world to rig coordinates. And we to estimate this camera calibration, we had the approximate 3D measured positions using a ruler. Because we placed this on the wall, we could like hand measure these coordinates. We knew that they were not accurate. We modeled that into the frame, unlike how standard calibration procedures are. In standard calibration procedures, the world frame coordinates are obtained and they are assumed to be perfect. In this particular case, that was also a free variable, which we accounted for. So doing all this, we could basically obtain a calibration which estimated the errors, taking into account the error of the calibration as well. So we got this, and then we estimated the true 3D world positions of the calibration target as well. If you want to see more details and more examples of videos like this for more sensors like a LiDAR or an inertial measurement unit or visual inertial SLAM, please drop a message and a comment in the video description, and I would really like to make more videos depending on what you would want to watch. And the final rig for our dataset had a couple of sensors. We had 2 Tango tablets, just like what you saw before. We had 3 GoPros for the ground truth. We had a visual inertial sensor, VI sensor, which had a stereo camera pair, global shutter, which was hardware synchronized along with an IMU. And then we had an Intel NUC for handling on the data processing, and we had a big chunky battery which was there, which we were powering the entire thing. And this is me carrying around the rig and walking very slowly so that not to upset any of these sensors. The way we did this was we said one of the April tags was basically decided as the global frame of reference, and then we would basically walk slowly enough that the same tag would appear in the next one, and so that there was some commonality between the neighboring frames so that we could basically map this entire thing. So as we kept doing this, we wanted to basically build a factor graph for pose estimation. This is similar to what we saw in the calibration case, but we are going to go into more detail so that it's easier to understand what's happening. Since we assume that the robot starts at x0, the map is at 0, 0, we are going to model that with a prior factor, which is going to be the initial pose, which is at 0, 0. And at state x0, we basically see that a bunch of April tags, let's say 4 of these landmarks, and the 4 corners of the landmarks, and this is obtained through the projection factor, which is that the world points are projected onto the image plane through the simple camera imaging model, right? And we know that each of these landmark positions, the 4 tag corners, are linked to each other through the size of the April tag, which is going to be these things called the between factor. We know that the tag corners in the world are of a particular fixed size, and that's what the between factor is. And since we also knew the world chosen origin, we basically had picked one of the tag corners as the origin. That's what the prior factor is. And the initial post prior factor is basically where we started from the odometry, which is 0, 0, 0, right? And then since we go from point x0 to x1 in time 0 to 1, we had to obtain the odometry. Because we were trying to get the ground truth, we did not have the odometry. And remember, I said that we were walking very slowly. That is modeled through the between factor, which is saying that the movement from x0 to x1 is identity, which is I did not move really fast. And we of course had a bunch more landmarks which could have been seen. And we basically did this and we extended this to multiple landmarks and multiple time steps, and we tried to optimize the entire giant thing in one go, right? This is what the actual factor graph looked like because it had the tag frame and the 3 cameras, and what you saw before was a simplified model. When you do that, if you take the floor plan and lay out the April tag locations which are estimated and basically the ground truth trajectory, you see that it aligns pretty well. As a fun fact, we also found there were a little bit of errors and mismatch between the actual building and the floor plan because of the construction error, and that's how accurate our model was. So it was accurate to about less than 10 centimeters error, which is great, right? And in this particular case, we had hand measured these April tag locations to get the initial guesses so that it would converge. But we could also do it in a way that like you don't need that. And that is basically the full SLAM method. And in this particular case, you will see like there are April tags in a bird cage and there is an aerial robot like flying around. And as you move around, you can see that it's like building a 3-dimensional map along with the poses shown in the coordinate frame on the right hand side here. And this is a framework you can download and use. It's called TagSLAM. This was built by Dr. Bernd Performer, who was the postdoc I was working with at that time when I was a master's student at UPenn. It's a great, beautiful package and it works really, really well and it's very robust. So instead of just performing a full bundle adjustment or full SLAM framework, which you might not always need, you might be okay with just doing something like odometry. The difference between SLAM and odometry is that in SLAM, you're also building a full map. In odometry, you just want to know how you have moved, right? And you don't really care too much about where the landmarks are. So, and that you can do with something called as ISAM2 or Incremental Smoothing and Mapping. In what we were seeing before, the full factor graph, you were trying to optimize the entire thing. In this particular case, your robot is moving from time 0 to time 1 through the odometry step. As you keep moving forward, you observe more observations and you get better and better. Here you'll see these ellipses, which are basically representing the covariance matrix. The larger the ellipse, the more uncertain you are about that position. As you will see, like as we keep moving around, the last point will basically be the prediction, so they'll have the largest covariance matrix. As we move around, the covariance matrices of the steps will keep reducing, right? And once you do take multiple steps, you'll see the covariance matrix actually reduces. The catch here is that ISAM is performing this at every one step. It's only taking the previous step and adjusting everything else. Instead of a full batch bundle adjustment or like factor graph method where you solve for the entire thing, you're only solving for the previous step. This is super useful because you can do this real time on a small robot, and which is generally enough for odometry. Note that this will drift over time because there is no final adjustment like we did before. You might be wondering, like, do I have to implement all this through math? Do I have to write the code for all this from the ground up? Fortunately, the answer is no. There are some wonderful libraries which you can use to implement these things, and all the examples we talked about were implemented using some of these libraries. All my thesis work was built on GTSAM. At that point, GTSAM 3.0 was the version which was there. Today we have GTSLAM 4.1, which is amazing and beautiful, and it has support for a lot of these sensor kind of data types. There is something called G2O, or General Graph Optimization, which is even more general than just factor graphs. You can use it for Bayesian graphs and things like that. There is also things called FGLib, which is basically a Python-based factor graph library. And these are all wonderful libraries which are very good to know and use in your robotics projects. Just to quickly recap, why do we need factor graphs when we have Bayesian graphs which are so amazing and beautiful? What is it that the factor graphs give you something extra? What is the key difference or the main difference between the factor graphs and the Bayes networks or graphs? What is one major thing that actually sets them apart, though they can achieve similar things? What is TagSLAM and how is that useful? How can you use that in the real world? If this video was interesting and you would want to watch more videos like this with factor graphs and more examples, please drop a comment on the video and I'd be really happy to make more videos on that. See you next time. Take care. Bye-bye.